What specific problem does MMSearch-R1 aim to solve, particularly in the context of information-seeking vision language tasks?
MMSearch-R1 aims to address the limitations of existing large multimodal models, LMMs, in handling complex and dynamic real-world knowledge, particularly in information-seeking vision language tasks. Specifically, it targets the challenge of effectively integrating external search tools to retrieve up-to-date information when models encounter unfamiliar visual content or previously unseen textual information, which often leads to hallucinations and unreliable outputs. The model is designed to learn three key search-related abilities: when to search, what to search for, and how to reason over the retrieved results to answer user queries accurately. By employing end-to-end reinforcement learning, MMSearch-R1 enhances the model's capability to perform on-demand searches, thereby improving its performance in knowledge-intensive visual question answering (VQA) tasks, while reducing unnecessary reliance on external information. Ultimately, this approach ensures that LMMs can adaptively and efficiently engage with real-world search environments, enhancing their usability in practical applications.
How does the proposed MMSearch-R1 algorithm work? Illustrate the methodology step by step, including how it integrates reinforcement learning with search tools for multimodal reasoning.
The proposed MMSearch-R1 algorithm integrates reinforcement learning, RL, with multimodal search tools to enhance visual question answering VQA capabilities. First, it constructs a multimodal search VQA dataset, factual VQA, FVQA, which includes both search-required and search-free questions, ensuring a balanced representation of knowledge types. Next, the algorithm employs a real-world search pipeline that consists of an image search tool and a text search tool, allowing the model to retrieve relevant information based on user queries. The core of the methodology involves the Group Relative Policy Optimization (GRPO) algorithm, which enables the model to learn when to search, what to search for, and how to reason over the retrieved results through an iterative multi-turn process. Finally, the RL training incorporates an outcome-based reward system that combines accuracy and format scores, guiding the model to effectively utilize its internal knowledge while invoking search tools only when necessary, thus optimizing its search behavior in real-world scenarios.
Can you provide a simple yet illustrative example to demonstrate the inner workings of MMSearch-R1? Walk through the main steps involved using a hypothetical question and image.
To illustrate the inner workings of MMSearch-R1, consider a hypothetical scenario where the model is presented with an image of an unfamiliar aircraft and the question, what is the model of the aircraft shown in the image? The process begins with the model analyzing the image using its integrated image search tool, which retrieves the TOP5 visually matched web pages. The model then evaluates whether it can answer the question based on its internal knowledge. If it determines that it lacks sufficient information, it generates a text query, such as identify the aircraft model in the image, and invokes the text search tool to retrieve relevant textual information from the web. After receiving the search results, the model summarizes the content and reasons over the retrieved information to formulate a final answer, which it presents in the required format. This iterative process allows MMSearch-R1 to effectively decide when to search, what to search for, and how to utilize the retrieved information to answer the user's query accurately.
What are the theoretical or practical benefits of using MMSearch-R1 compared to traditional approaches like retrieval augmented generation, RAG, or prompt-engineered agents?
Theoretical and practical benefits of using MMSearch-R1 over traditional approaches like retrieval augmented generation, RAG, and prompt-engineered agents include enhanced efficiency and adaptability in search behavior. Unlike RAG, which operates on a fixed retrieve then generate workflow and often leads to over-retrieval and high computational costs, MMSearch-R1 employs end-to-end reinforcement learning, RL, to teach models when to search, what to search for, and how to reason over search results, resulting in a more targeted use of external information. Empirical findings indicate that MMSearch-R1 outperforms RAG-based models of the same size by an average of 3% in accuracy, while reducing the search rate by 32.9%, demonstrating its ability to achieve higher correctness with less reliance on external data. Additionally, MMSearch-R1's RL framework allows for dynamic interaction with real-world search tools, enabling the model to adapt its behavior to open-world environments, which is a limitation in prompt-engineered agents that do not optimize model parameters through learning. Overall, MMSearch-R1 provides a more robust solution for knowledge-intensive and information-seeking tasks, ensuring practical usability in real-world applications.
How was MMSearch-R1 validated or tested, specifically detailing the datasets used, experimental setup, and performance metrics to assess the method's effectiveness?
MMSearch-R1 was validated using a comprehensive experimental setup that involved multiple datasets, including FVQA test, InfoSeek, MMSearch, Simple VQA, and Live VQA, to evaluate its performance on knowledge-intensive and information-seeking VQA tasks. The model was trained on a dataset consisting of 5,000 samples, with a balanced distribution of approximately 3,400 search-required and 1,600 search-free examples, ensuring diverse knowledge categories and question difficulties. During testing, the model's responses were assessed using the LLM as judge framework, where GPT-4o evaluated the correctness of the answers based on the original image, question, and ground truth answer. Performance metrics included accuracy, the search ratio, the proportion of responses invoking a search, and comparisons against both closed-source models like GPT-4o and open-source models from the Qwen 2.5VL series. The results indicated that MMSearch-R1 to 7B outperformed RAG-based counterparts by an average of 3% in accuracy, while reducing the average search rate by 32.9%, demonstrating its effectiveness in on-demand search behavior.
What limitations or drawbacks did the authors acknowledge regarding MMSearch-R1, and how might these impact its application in real-world scenarios?
The authors acknowledged several limitations of MMSearch-R1, particularly regarding its reliance on static training data and the challenges of integrating real-world search interactions. They noted that existing approaches, including retrieval-augmented generation (RAG) and prompt-engineered agents, often operate under fixed workflows that do not adapt well to the dynamic nature of real-world scenarios, leading to inefficiencies and potential inaccuracies. Additionally, while MMSearch-R1 improves on-demand search capabilities, it still faces challenges in constructing suitable training data for multimodal contexts and optimizing reinforcement learning frameworks for effective real-world interactions. These limitations could hinder the model's performance in knowledge-intensive tasks where up-to-date information is crucial, potentially compromising its reliability and trustworthiness in practical applications. Furthermore, the model's ability to handle complex queries may be restricted by its training on a limited dataset, which could affect its generalization to diverse real-world situations.